All right, let's go ahead and do video example number 3 for series. The problem says the Maclaurin series for the natural log of 1 plus x is given by, and then it lists out the first 4 non-zero terms in the general term for that series. On its interval of convergence, the series converges to the natural log of 1 plus x. Now it says let f be the function defined by f of x equals x times natural log of 1 plus x over 3. Now for A, it wants us to write the first 4 non-zero terms and the general term of the Maclaurin series for f. So we want the Maclaurin series for this. Now, because we're a Maclaurin series, we're centered at 0, and we can use a series like natural log of 1 plus x to be able to help us find x times the natural log of 1 plus x over 3. We're going to do that by taking x over 3 and plugging it in for x, and rewriting our series, and then taking that series and multiplying it by x, because these two are equivalent. So let's go ahead and do that step by step. I'm going to go ahead and take x plus 3 and substitute it in here first. So I'm not going to be able to label my series f quite yet. I'm just going to be able to call it, natural log of 1 plus x over 3. And I'll be able to substitute in my x over 3 here for my terms for x. So instead of x, I'll have x over 3 minus, instead of x squared, x over 3 all squared divided by 2 plus x over 3 cubed over 3 minus x over 3 to the 4th over 4 plus dot, dot, dot. Now, the same goes for the general term, right? This is just an extension of what our series was over here. So I'm not going to touch the alternator. I'm not going to touch the denominator of n, just like I did over here. And now I'm only going to plug in x over 3 for my numerator, x to the nth power. So I'll end up with what? Negative 1 to the n plus 1. Now, x over 3 to the nth power over n plus dot, dot, dot. Now, we're not to the series for f quite yet, right? I've just taken x over 3 and substituted it in. Now I need to go through and multiply my series here by x. So to get f of x, or x times the natural log of 1 plus x over 3, I'm going to take x and multiply it by all the terms on this side of the equal sign as well. So x will become x squared over 3 minus, let's do a little bit of cleaning up here. Before I actually multiply by x, I'm going to take this 3 to the second into the denominator here and multiply it by 1/2 from the denominator here. So my denominator is actually going to be 3 to the second times 2. X to the second times the x that I'm multiplying by is now going to be x to the third. Plus, I'm going to do the same thing here again, okay? My denominator is going to be the 3 from this denominator times 3 to the third power from here. So I'm going to say 3 to the third. When I multiply through by x, x to the third power times x becomes x to the 4th. Again, I'm going to try and manipulate my denominator first. I'll end up with 4 from the denominator times 3 to the 4th. X to the 4th power times the x becomes x to the 5th. Plus dot, dot, dot. My alternator is not going to switch here, so I'm just going to copy that down. Again, because I didn't take the time to simplify this before multiplying through by x, I'm going to have to manipulate my denominator. So n times, I guess it's 3 to the n, right? And this will be x to the n, but then we're multiplying by an x to the first. So x to the first times x to the n. So maybe I'll write that down here. Adding my exponents will give me x to the 1 plus n, or n plus 1, plus dot, dot, dot. And there's our series, the first four non-zero terms, plus our general term. Now, this general term is going to be important when we get down into the letter B here. So let's go ahead and jump down into that one. It says, determine the interval of convergence of the Maclaurin series for F. Show the work that leads to your answer. So, interval of convergence for F means I want to run the ratio test on this general term right here. So to run the ratio test, I'm going to take the limit as n goes to infinity of the absolute value. So when I start my ratio test down in letter B, the absolute value of my alternator is going to be turning all of my terms positive. So I'm just going to leave off my alternator when I write it down here. So let's go ahead and jump into that. I'm going to start with the limit as n goes to infinity of the absolute value of the nth plus 1 term. So I'm going to plug n plus 1 into all three n's. So I will end up with x to the n plus 1 over, instead of n, I'll end up with n plus 1 times 3 to the n plus 1. Now, we would normally divide by the general term here, right? We want each successive term to be smaller and smaller, but I'm going to go ahead and show it as a multiplication by the reciprocal. So I'm going to have n times 3 to the n over x to the n plus 1. Now let's do some simplifying here. That looks fairly complex. So limit as n goes to infinity. I'm going to start here with my x term. X to the n plus 1 is really x to the n plus 2. And if I subtract the denominator, the exponent of the denominator for my base x, n plus 2 minus n plus 1, the n's will simplify out and I'll just end up with 2 minus 1, which is just x to the first power, so x in the numerator. I see a similar simplification strategy here with my 3, base of 3, n minus n plus 1. The n's will simplify out and I'll be left with negative 1, or a 3 to the first power in the denominator. And then the only two terms that I have left is n over n plus 1, and those aren't like terms. I'm not going to be able to simplify those out. So I'm going to put, I guess I'll put these in parentheses, n times n plus 1. So simplifying this has really helped me out. I think it's easier to see what's going to happen now as n goes to infinity. Remember, x we're treating just kind of like a constant at this point. So I'm only looking at my n terms. I have an n to the first in the numerator and an n to the first in the denominator. As we go to infinity, those are going to be the same sort of infinity and really kind of simplify themselves out. So I'll be left with just my constants of x over 3. And ratio test will converge when this value is going to be less than 1. So I like to take care of the absolute value. So we can say that what's inside the absolute value will be less than the positive version of that, but also greater than the negative version. So we'll end up with an extended inequality of negative 1 is less than x over 3, which is less than 1. And again, that's because our variable over here is less than 1, right? If the inequality sign was flipped, we'd do the, this would be less than the smaller value and then greater than the bigger value, right? And we'd put that big old or in between them. But we get an extended inequality here, which if we multiply by 3, we can get our interval where this series is going to converge, or the beginnings of our interval. Now, ratio test, remember, when we equal 1 out here, all right, it's an inconclusive test. So it's good to give us a general idea of what our interval is going to be, but then we need to take the x equals -3 and the x equals +3 to be able to test those endpoints, to be able to see if the endpoints actually converge. So we need to test that. And again, well, let's do x equals 3 first. We'll do x equals -3 second. We're going to use our general term up here to be able, oh, can't see that, our general term up here to be able to help us out. So our summation starts when n equals 1 over here. So let's go n equals 1 to infinity of -1 to the n plus 1 times, now instead of x to the n plus 1, this is where 3 comes in, right? 3 to the n plus 1 all over n times 3 to the n. Again, I see a little bit of simplification here, so I'm going to pretty this up a little bit. -1 to the n plus 1. I think I'm left with a factor of 3 in the numerator over n. And we have an alternator. We have an n to the first. If I take the limit of this as we go to infinity, we'll definitely go to 0. So I could write the limit as n goes to infinity of our series here, of our simplified series. That's going to be 0. So therefore, this will converge by the alternating series test. So AST. So down here for our interval, we can add the equal to sign to 3 because when we plugged in 3, we converged. Now let's go ahead and test over here at -3. If x equals -3, we still have the series starting at 1 going to infinity. Still have -1 to the n plus 1. But now instead of 3 to the n plus 1, now we're going to get -3 to the n plus 1 all over n times 3 to the n. Now, this piece looks very close to this one. I'm going to go ahead and rewrite this. I'm going to just say that this is -1 to the n plus 1 times 3 to the n plus 1. Okay? They have like base, or because they're to the same exponent, we can split the bases in this fashion. And now I think 3 to the n plus 1 over 3 to the n, I'm going to get a simplification like before, right? Where I end up with the additional factor of 3 in the numerator. Just like before, n in the denominator is going to stay there. But let's take a look at what happens here. -1 to the n plus 1 and -1 to the n plus 1, they're like bases, so I can add these two together. That ends up being -1 to the n plus n, which is 2n, and 1 plus 1 is 2. Now, if I were to plug in successive values of n here, 1, for instance, let's start with, that would be 2 plus 2, which is 4, which is an even number. If I plug in 2 for n, 2 times 2 is 4, plus 2 is 6, which is an even number. Oops, this is -1. If I plug in 3, 3 times 2 is 6, plus 2, which is an even number. Each value, or each number for n that I can plug in here for this series is going to end up with an even number. And -1 to an even power, it's just going to be +1. So our alternator is really just equal to +1. We can say that this series is from 1 to infinity of 3 over n, which, n to the first, you can recognize it as a divergent harmonic series, or a p-series, whichever one suits you best. This one is going to diverge, and I'll say the divergent harmonic series. If I could spell. And because this diverged, x equals -3 is not convergent, so that my interval is from -3 open to +3 closed.